Hi guys, welcome. So today we are going to move on with our advanced calculus lessons, and today's topic will be on the arc length and the arc length parametrization. So far, what we have studied is we have introduced space caves, and we have actually also introduced the normal vector, which is an object that tries to measure the velocity of the object that is tracing the space curve itself. Because remember, we say space curves are curves that have a physical meaning behind them, which means they can be used to depict the motion of a moving object. And already we have shown that if indeed you have a space curve that is being traced out by a moving particle, how can you determine the direction the particle is moving instantaneously? And we have seen that this can be done by what is known as the unit normal vector. So today we are going to shift our focus into something different. So what we're going to look at is, suppose we have our particle which is tracing out some motion in three-dimensional space. You see that? So if we're to mark like 2 points along this curve, let's say point A and point B, the question that we're interested in now is how can we determine how long it took the particle to move from this point to that point? So this is what we are going to try and see how we can measure that distance. So we refer to this distance between 2 points along a space curve as the arc length. So when we talk about arc length, that's definitely what we are going to be referring to. And the symbol that we use to refer to an arc length of a particular space curve, we denote it by the small letter s like that. So this is convention that is used in many books, but you can use any symbol that is suitable as long as you explain what is the meaning of the symbol that you'll be using, you see. So yeah, that's what we are going to learn today, how to determine the length of an arc of a given space curve. So to actually measure the length of an arc of a given space curve, one way is to just start from simple basic that everyone knows from primary and see how we can shift to the language that we're using currently. So we know most of the time that every time when I'm interested in measuring distances, I know that I'm aware of this formula that speed is equivalent to the distance over the time taken to cover that distance. So that's one thing that we know most of the time, that if you're given a curve, we know that speed is actually given by that, you see. So this implies now what we have to do is how can we then convert this to the language that we're using currently. So which means now in terms of the objects that we're dealing with, it, which are the space curves, how can we actually find analogous terms that can replace all these things, you see. So in terms of the vector language, the thing that allows us to measure what we call speed velocity is actually the derivative of the position vector itself. So every time when you want to find an object that can play the role of velocity, then you can use that object. But since we were talking about speed, it means we need its magnitude. So we'll just find the absolute value of that position vector as it changes time, like that. Then the role that is going to play the distance that you are measuring is the length of the curve itself, which I'll just say the change in position, and then this over the change in time, you see. So we can see that from what we have written here, we can see that what is known as the speed object is the same as just saying the distance over the time. So if we can make ds the subject from that, we can see that ds is simply r prime of t dt. So I can now integrate these both sides to get my arc length that I'm looking for. So therefore we can now see that if I integrate on the left hand side, I can observe that I obtain S, which is just the integral of r prime of t dt. You see, and most of the time, since we're always interested in measuring the length of a curve from between two particular points, then you will find that this integral will be from the limit a to b, since most of the time the parameter t that we always use in problems always ranges between some values a and b, like that, you see. So which means what we call the length of an arc of a curve is actually given by this formula. So every time when you want to find the length of an arc of a curve, this is how one can simplify it. You just have to make use of this formula that we have just derived simple from basic fundamentals that we know from primary, like that, you see. So every time when you're interested in finding the length, this is how you go for it. So what we're going to do now is we're going to now see how exactly can we make use of this formula in finding length. You see, that's what we want to see now. So one of the things that we have to do now is we have to recall some things that you might need at this instance. So recall that if r of t is defined as x of t, y of t, z of t, then what we call the absolute value of r prime of t is just the same thing as saying square root of x prime t squared plus y prime t squared plus z prime t squared, like that. So these are things that you should know. What is the meaning of the absolute value of r prime t? It has the same meaning as that because r prime t is a position vector whose components are always xt, yt, and z of t, like that, you see. So now the question is, how can we use all this to find the length of an arc of a curve? So now it's time to look at examples and see how we can solve such problems. So the first example that we have, it goes as follows. Given a curve C such that as r of t is equals to 2 sine t root 2 t 2 sine t root 2. So given a curve such that r prime of t is that with t ranging from 0 to pi over 2, determine the length of an arc of this curve that starts from the point 2 pi over 2 root 2, 0 to the point 0 pi over root 2 to minus 2. So this is the problem that we want to deal with now. So we're given this problem and we want to find the length of the arc of a curve which starts from here to there. But first, let me clarify something. Actually, what I wrote here is the limit. So the length of the arc of a curve is not calculated actually using these limits that I wrote there. So it's wrong to put these. So let me take these out. So the limits of integration, they are not actually the bounds of the parameter t, but they are subintervals of the parameter t. So it will be good maybe to represent them as just a prime, b prime. You see that? Such that the interval from a prime to b prime is a subinterval of AB, like that. So this is one thing that you should make sure that you understand, that the limit of integration every time when you're finding the distance, they are not the bounds of the parameter t, but it's a subset that lies within the interval of values for which the parameter t can take. So it's good to make clarity of that before we solve this problem. Because you can see now that this problem, they are saying that we should find the length of an arc which starts from a particular point A, which let's just call this point A, and to a particular point B, like that. So the question now is, how can we solve this problem? So first, let's understand exactly what are we trying to do here. Because every time when you have to solve a problem, it's good to always understand exactly what is your goal, what are you trying to achieve. So let's see what exactly are we trying to achieve. So let's try to represent this in three-dimensional space. So we have x, y, and z, 0. So we have a curve that we are not familiar how it behaves, but what we know is that we do have a curve. And in this curve, there are 2 points, which I'll label in red, A and B, which lie somewhere along the curve like that. So what we are interested in is what is the length between these 2 points. You see, so what is the length between these 2 points, which we'll refer to as S. And remember, the point A is, as given in the problem, it's 2 pi over 2 root 2, 0, and the B is, in this case, 0 pi over root 2, then minus 2. So this is what A and B are in this problem. So the question now is, how can we find the length of this curve? You see, so before you know already the formula that you're going to use for finding the length. So every time when you're given this problem and you are asked to find what is the length of a portion of a curve that is given, you have to make sure that you are able to see the limit that you're going to use for your integration. You see, so first, that's what we're going to do. We're going to see how we can establish the limits that can be used to integrate our problem to get the required distance. So to do that, I will invoke the object that plays the description of this curve. So now what are we told? So we are told that r prime of t is being defined as follows. So it's 2 sine t root 2 t, then 2 cos t root 2. So that's what we have, like that. So r of t is given like that. So what we should check now is if you can be observant enough, you can see that the Mickle coordinate is just t itself, which is the parameter itself. You see that? So now let's go and check now how exactly does one establishes the given limits, or the limits that you need to perform the integration. You see that? So if you are looking for the limits that you are going to use for integration, this is how you go about it. So what you should know is that all the points that lie on this curve, because remember this curve, it consists of many points that lie on top of it like that. You see? So there is a specific parameter that specifies each and every point that lies on that curve. You see? So the thing that we should now do, or we should ask ourselves, is what are the parameters that corresponds to these points that are given? So for these points that are given, which is this A and this B, what are the parameter values that correspond to that? You see? So you will see that if you come and study here, you will see that already the y component of our position vector seems to be exactly the parameter that describe all the points that lie on this curve. Which means if we can study how y is changing, we can be able to tell what parameter was used to establish this point. So definitely from that, we can see that the parameter that corresponds to this point below is just the parameter t is equals to pi over 2 root 2. Then again, if you do the same thing here, you will see that the parameter that corresponds to that is t is equals to pi over root 2, because we see that if the length of the curve that is changing from A to B, the parameter is changing from having this value to having that value. So which means we can see now that this is our limits of integration. We are integrating from pi over 2 root 2 to pi over root 2. So now, knowing our limits, it's time now to see how we can deal with our problem. So now we need to differentiate this. So let's differentiate to find r prime of t. So what is r prime of t? If we differentiate this, we can agree to say that this is going to give us something like 2 root 2 cos t root 2. Then if I differentiate inside, I get 1. Then here I'll get negative 2 root 2 sine t root 2, like that. This is what we observe. Now we need to know what is the magnitude of this expression, you see. So this implies what is the magnitude of this r prime of t, because that's what we need for our formula. So the magnitude we know is given by 2 root 2 cos t root 2 all squared plus 1 squared plus 2 root 2 sine t root 2 all squared. So if we simplify that, what we obtain? So we see that if you square this thing on the inside, you will have something like this. So you will have a 4 by 2, which will give us 8 cos squared t root 2 plus 1 plus 8 sine squared t root 2, like that. So the trig functions, I can pull out the 8 and group them together. So if I pull out the 8 and group them together, I get cos squared t root 2 plus sine squared t root 2. Then plus the 1 that is remaining. But recall, cos squared plus sine squared is equivalent to 1, which means this will just simplify to root 9, which will then give us a 3, like that. You see. So now knowing this, it therefore follows that the distance that we're looking for, which is s, is given by the integral from pi over 2 root 2 to pi over root 2 of r prime of t, of the absolute modulus of r prime of t, which is 3 in this case, dt. You see. So therefore what we get for our distance, so we see that our distance is just 3t, with t ranging from pi over root 2 to pi over 2 root 2, like this. So what happens now? So we get 3, and then we get pi over root 2 minus pi over 2 root 2. So therefore what is s? So when we simplify this, we can see now that the final solution is going to be what? So it's going to be 3 pi over 2 root 2. So this becomes the length that we are looking for, like that. You see. So this is how you go about finding the length of any arc of a space curve in vector calculus. So it's very important to know how to work out quantities like these. So let's do another example, because sometimes one example may not be sufficient to get fully what's going on here. So let's look at another question again. So given the curve C such that r of t is equals to 1 plus 3t squared and 4 plus 2t cubed, with t an element of real numbers, determine the length of the arc from the point 1, 4 to the point 4, 6. You see, so I like this problem because it is a bit more general and much trickier than the one that we have seen already, because you cannot see just the intervals of integration just by inspection. You will have to work to actually achieve them. So I'll show you how exactly we can actually attain the intervals of integration in a problem like this. You see, so how do we then solve this problem? So remember, every time when you want to solve a problem, it is always good to actually have a sketch nearby so that at least you understand what's going on. So what's going on now is that we have a Cartesian plane like that, and there is a curve like that. So inside this curve we have 2 points, but remember this is actually a two-dimensional problem. So what I did now actually does not reflect truly what way you are dealing with, because if you look closely you will see that this is a two-dimensional problem. So since this is two-dimensional, let's not complicate things by drawing it in a three-dimensional space. So what is happening is that we have something like this. So we have y, 0, x, and inside this 2D space there is a curve. I don't know how it's BF, but it might be something like that. So what's going on is we have 2 points, one sitting there, and then I'm not drawing them accurately as they are shown. I'm just trying to represent them what they like. So we have 1 point, and their labels is the other one is 1, 4, and the other one is 4, 6, like that. You see, so this is a rough sketch. So it's not showing exactly the true geometry of the curve and also the true location of these 2 points. So it's just a rough sketch. So because we want to just get the idea. So remember, each and every point that lies along a space curve can be characterized by a specific value of the parameter. So what we have to know now is what is the parameter value that corresponds to this point and what is the parameter value that corresponds to that point. So how can we establish that? So if you want to establish what parameter values correspond to this point, first you will have to invoke the position vector itself. So what do we know? So we know that r prime of t is equal to 1 plus 3t squared and 4 plus 2t cubed. So that's one thing that we know. You see that? So in order now to establish what parameter values correspond to this point, what you do is you first take this, because remember this object, it is a general point. So this object that we have here, it is just a general point along the curve. So this object, you have to understand what it is. So it represents any general point that lies along the curve. So every time, if you want to know if a particular point belongs to this curve, you can substitute it and check if there is a balance there. But what we want to do now is we know that if we are given that certain points like this one here belong to a particular curve, then there must be some parameters that can produce those 2 points. So what we have to do now is to figure out what parameters can be substituted here to obtain those 2 points. So to do that, this is how we do it. You see, so we come and say if 1 plus 3t squared 4 plus 2t cubed is equal to the other point, let's say for now 1, 4, what happens? You see, so if this is equal to 1, 4, we agree that 1 plus 3t squared is to equal to 1. So we see that 3t squared is equal to 0. So therefore we see that this point corresponds to a parameter value of 0. You see? So again, if this point 1 plus 3t squared 4 plus 2t cubed is equal to that other point, which is 4, 6, what happens? So remember, every time when you want to find parameter t, you can use any of those two components. So me, I used the x components. I equated the x components to establish the t value of 0. So even here again, your choice is yours. Which one would you prefer to work with to obtain what the parameter value is? So I can choose the y component. So from the y components, I have that 4 plus 2 t cubed is 6. Then for that side, I get t cubed is equals to 1. Cube rooting, I get t is equals to 1. So I see now that these points that are given, they correspond to the parameter values of 0 and 1. You see, so which means every time when you need this particular point, this is established by t0. When you want that particular point, this is established by t equals to 1. So now knowing our interval of integration, now it's time to find the distance. You see, so to find the distance, what we do now is we differentiate our position vector to get r prime of t, which is equal to what? So if we differentiate that, if we have the question with you, you will see that you get 6t and also 6t squared. So that's what we get when you have to differentiate. So this implies now what is the absolute value of r prime of t. So the absolute value of r prime of t is root of 6t squared plus 6t squared squared, like that. So simplifying, we see that inside we'll have 36t squared plus 36t4. But 36t squared seems to be common, so we pull it out, which way it comes out as 6t root of, inside will remain with 1 plus t squared. So which means that's what we're looking for. So therefore now what is the length of the arc that we're looking for? So the length of the arc that we're looking for, S, is equals to the integral from 0 to 1 of the absolute value of r prime of t dt. So what does that give us now? So it is the same thing as the integral of 0 to 1 of 6t root of 1 plus t squared dt. So how can we deal with this? So now it's back to our freshman maths. So let's see now how we can deal with this. So to deal with this now, we can use many of the techniques that we know. So I'll use preferably the substitution technique because it is the most suitable technique to use now. So to do that, we proceed as follows. So we'll say let t squared be equal to u. So this implies 2t dt is equals to du, like that. So I can multiply by 3 both sides. If I multiply by 3, I get 6t dt is equals to 3 du. So having all this with me, also I can change. Since I'm changing my variable from t to u, I also have to establish how my limits will change in that situation. You see that? So we see now that if t is equal to 0, u is equals to 0, and if t is equals to 1, u is equals to 1 again. So our limits, they don't change. So therefore now what is the length that we're looking for? So therefore it follows now that the length of the arc is just the limit from 0 to 1 of 6t dt, which is 3, then root of 1 plus u du, like that. So we can all recognize that this can be written as integral from 0 to 1 of 1 plus u to the power half du. So now we know the rule of how to integrate something like this. So to integrate something like this, we know that we increase the exponent by 1, which will give us 3 over 2. And then we bring down that as a denominator to get that, and then we integrate from 0 to 1, like that. So we now see that all this will just simplify to become 2, 1 plus u to 3 over 2 from 0 to 1. So therefore, what is S? So what is S? So first we put 1, so we get 2 to the power, what? So root 2 cubed. Then we put 1, so we just get minus 2. So you can either leave your answer like this, or you can see if you can put it in a much nicer form than this. But yeah, I'll just leave it there. So this is how you can actually find the distance or the length of an arc of a given space curve. You just have to make use of this formula that you have seen already, and the rest is just a test of your integration. So you just have to apply your integration skills to see how you can actually find that length. You see. So the next thing that we want to look at now is what is known as the arc length parametrization. You see, so what exactly is the arc length parametrization? You see, so I can say the arc length parametrization, it is just the act of changing the parameter of the space curve. You see that? So it's more like trying to shift from r of t to get to r of s, where s is the arc length. So that's what this parametrization is all about, because the position vector is always defined in terms of the parameter t, but it's not only t that can be used to parametrize curves. So curves, they can also be parameterized using arc length in such a way that every time when you move a particular distance along the curve, you can be able to tell where you are from the length that you have traveled. So that's why this parametrization is quite important, because every time when something is moving, when it is moved a particular distance, there is always that interest of knowing where exactly are we located at this instant. So in order to change the parametrization, this is what we call the arc length parametrization. So now we'll see exactly how one can actually change the parameter of a space curve from being t into being the arc length s. You see that? So in order to do this, we should now recall the following. You see, so what you should know is this. So if we have that, if we have some position vector r of t with t ranging from a to b, then you should know that the following is true. So the integral from 0 to s of ds prime is the same thing as the integral from a to b of r prime of t dt, like that. You see, so these are things that you should know, that this thing that we call the arc length, it is actually equivalent to this. It is actually equivalent to this. So this can help us now in transforming the arc length parametrization of a curve. It can help us in doing that. But in order to do so, actually, if I were to put the top, if I were to put the top integral to sit exactly at b, we all can agree that the integral on the right hand side will actually evaluate into a number, which is not exactly what we want. So what we have to know now is that for now, I will not integrate from a to b, but I will integrate from a to t, where this is just written as r prime of t prime dt prime. So this is the formula that we need every time when we are to perform the arc length parametrization. You see that? So what this formula is trying to tell us is it on the right hand side, what we have is you have the measure of the length of the arc from the starting point of the parameter A to some parameter value T that lies between A, B, like that. So B, the end B hasn't yet been reached. So when the parameter is changing from small value, from the least value A to some value, what distance have we traveled is given by the expression on the left hand side. You see that? So this thing is more like every time when T changes instantaneously, this updates the distance that has been traveled. So in order for us to perform an arc length parametrization, it would be good to invoke this definition. You see that the integral from 0 to s of ds prime is the same as saying the integral from a to t of r prime of t prime dt prime. You see. So yeah, these are some things that we have to know. So now what we're going to do is we're going to see how then we can then change the parameter by making use of this result. So to do that, we are going to look at the following example. So the question goes as follows. Find the arc length parametrization. Find the arc length parametrization of the curve. Find the arc length parametrization of the curve r of t, which is equal to 3 cos t, 3 sin t, and 4t, where t is an element that ranges from 0 to 2 pi. So how can we find the arc length parametrization? So how can we change the parameter from being t to being s? That's the question that we want to answer now. So to answer this question, this is how we proceed. You see, so at first we invoke what we know. So recall the integral from 0 to s of ds prime is the same as the integral from not from 0, but from a to t of r prime of t prime dt prime. That's one thing that we know, that this result that you have here is true. You see. So now how can we make a use of this then to perform the arc length parametrization? So it means to perform the arc length parametrization, first I need r as a function of t prime. You see. So I need r as a function of t prime. So now what do we see? So we know that r as a function of t prime is just the same as saying 3 cos t prime, 3 sin t prime, and 4 t prime, like that. So now what we're going to do is we're going to differentiate this. So to differentiate this, we see that it's going to give us r prime of t prime, which is going to be negative 3 sin t prime, 3 cos t prime, and then 4, like that. Then now we find the magnitude of this result. So what we get now when we calculate the magnitude of this result, so it follows from here now that the magnitude of r prime of t prime is equal to negative 3 sin t prime squared plus 3 cos t prime squared plus 4 squared, like that. So what happens then? So we see now that if we square that, we get 9 cos squared t prime plus 9 sin squared t prime plus 16. But we know that 9 sin cos squared plus 9 sin squared is going to just be 9. So we have 9 plus 16, which is 25, and root 25 is 5. So we see that the absolute value of r prime of t prime is equals to 5. So now if we were to substitute back to our main result at the top there, what does that imply? So it then follows that the integral from 0 to s of ds prime is equal to the integral from, since a in this case, a, remember, it always refers to the lower limit of the bound of t. So t is bounded between 0 and 2 pi, so our a is 0 in this case. So we are integrating from 0 to t of r prime, a modulus of r prime of t prime, which is 5 dt prime. You see. So now what happens from here? So if we integrate on the left, we see that we just get s prime, which varies from 0 to s. And if we integrate on the right hand side, we get 5t prime, which also the limits are ranging from 0 to t. So therefore, what follows from here? So we can see now that if you put s here, you'll get s is equals to 5t, like that. So this gives us now a relationship between t and s. So which means we can see that t can now be actually replaced by s over 5. So now we have to go back to our curve, and wherever we see t, we replace that with s over 5. So therefore, what we get? So we see now that we have now r of s over 5, which is equal to what? So wherever there is t, we put that. So we get 3 cos s over 5, 3 sine s over 5, and then 4s over 5, like that. So this is the arc-length parametrization. So usually this function that we have here, it is always denoted mostly as gamma of s, like that. So because it's now a new position vector which varies in terms of the parameter s, like that. So you can then actually now call that as your arc-length parametrization. So this is how you can change the parameter of a space curve from the parameter t to the parameter s, where s represents the arc length. You see. Otherwise, yeah. Thanks you for watching, guys. So meet you next time, where we are going to be moving on with the discussion of space curve, trying to introduce a lot more concepts that are tied to the motion of moving objects. Okay, see you.